Hello everyone, I hope my sound is clear. So I'm going to have a quick review on what we discussed last week. We were looking at amplitude modulation. So this is another concept that is really related to wireless connectivity of Internet of Things. So I emphasize on parts that are more close to my expert area. But I know that many of you have nice background and you have the basic knowledge of how a signal can be modulated. So referring to last week, we need to modulate signal at transmitter, and when we are receiving a signal, we have to do demodulation. And the reason is because we want to extract that useful data containing information. And we can play around with the characteristic of carrier signal in order to have different types of modulation. The one that we looked at it last week was amplitude modulation, and we were changing amplitude of carrier signal according to our data containing or modulating signal. I will look at the waveform in a second. Then I explained that this is a type of analog modulation. Later on, we are going to look at digital modulation, and then you will see that it is slightly different because the data that is generated and wants to be transmitted, that type is different. The carrier signal is pretty much similar, but the nature of the carrier modulating signal is changing the new type. Now, just a quick review. On the top, I have my signal wave, the one that contains information, and the bottom one is the carrier wave. And after the transformation, after the modulation is done, I end up with a wave that looks like the one that I have here on, I don't know, is it your right side or your left side, depends to how I'm recording. Based on the slides that are on brighter space, it will be your right side. So you can see that the carrier wave is transformed, is changed. The amplitude of carrier wave is changed. The frequency of the carrier wave is not changed. It is staying the same. The amplitude is taking the form of the signal wave in a way that we can actually look at how to calculate the maximum of that wave, how to get the minimum of that wave. So the process involves two mathematical processes, if we want to look at that. We have a shift, so we are passing 1 into empty, if empty is our data containing signal or modulating signal. And by that shift, what is happening is the signal is avoiding crossing the 0. So we are removing the negative side, so everything is shifted up. And then the result of that is going to be multiplied in my carrier signal. A typical way of talking about carrier signal is always saying cosine of omega ct or cosine of 2p fct. So the frequency that is associated with the carrier signal is normally known as omega c or fc. And normally we say that MET is the modulating signal. So we have this multiplication. So when we multiply that sinusoid or result of many sinusoids, so you can see that shape is not actually sinusoid here. It's result of multiple of them. It can be a result of inverse fast Fourier transform. So many sinusoids are combined together to create that shape. It can have any random shape, to be honest. So when that is multiplied in our red color carrier wave, so we end up with this signal here. We have this modulated signal. You can see that when I try to draw it with similar looking frequency, so the red color frequency should be the same as the one that I have here. but the amplitude of that is reshaped. It's following the path according to my MT, and the reason is because I need that, and that is the information that I'm looking for at the receiver side when I want to extract it. That is the envelope of the signal that I needed. Now I looked at the mathematics. I explained that the result of that multiplication is going to give me this sinusoid ST here, if I can point out here. So this will be my modulated wave, modulated signal, and then I refer to this wave and I explain that the maximum of any sinusoid wave can be 1. So if we replace this cosine and that cosine with 1, you end up with AC plus AM, and that will give us the maximum value of the modulated wave. Similarly, we can find out, determine the minimum amplitude of this modulated wave. Now, we also looked at how that signal looks like from frequency point of view, and I explained that how it is different at signals from the angle that has time involved, from the angle that has frequency involved. So the one that you can see from the left side, and you can see those dashed lines, so that is indicating the envelope of the signal and the modulated signal. So it's AM modulated signal from time domain. We call it time domain when you're looking at the time angle. So one of the axes is actually indicating the time, another one is normally indicating the amplitude or magnitude. Now, if we are looking at frequency, we are looking at the spectrum of the signal. And normally what happens is our carrier signal is going to appear at some point as a spike. But because of the phenomena that I will explain further later on, we are going to have some side lobes. And those side lobes are associated, known as bandwidth. So I'm not going to look into only one spike when I'm looking at a frequency domain of a signal. I'm going to look at a boundary of frequencies. And that boundary of frequency is going to give me bandwidth. Definition of bandwidth is coming from here. Now, if I'm looking at one example, and the center of that spectrum, that boundary, the center of that is my carrier frequency. So I want to see how to measure that bandwidth, how far we can go. So a rough idea, it would be I will be from FC minus FM. So I will be on the left side for the amount of my frequency of modulating data, and on the right side the same amount as the frequency of my modulating data. So based on that, if I want to measure from the start to the beginning of my bandwidth will be equal to FC plus FM minus FC minus FM. So they will cancel each other and I will end up with 2 FM. It makes sense because my bandwidth shouldn't have anything to do with my carrier frequency. It should be associated with the type of signal that I am sending. So bandwidth is equal to double the modulating signal frequency. So I have this source here. It's a very nice video explaining about the frequency domain and time domain and how bandwidth is associated with those definitions. Go ahead and watch that. I remember I played a little bit of that in the class, but it was a long video, so I left it for you to watch later on. Yeah, this is one of the examples. If I'm not mistaken, I was explaining how those frequency elements can be associated with the time domain elements. That is also a nice video there. You can watch that, and if you have any question, just feel free to ask me in the next class. that, I'm going to skip over that. So here I am looking into analog modulation versus digital modulation. So when we were looking at modulations that are analog, our data, our modulating signal was naturally analog. Something like a sound, something like a music, something like a recording, that type of signal I'm looking at. And when it is combined with carrier signal itself is analog. So it is analog and analog, so we are calling it analog modulation. Now what happens if the nature of the signal that is being generated is digital? So I'm looking at a sort of sensor generated signal which is based on high and low, 1 and zeros. Or for whatever reason, we have transferred that analog signal to a sort of digital signal, which we know that if we want to store something, it has to transform to that digital form anyway. And then I want to use that digital form and modulate that with the analog carrier and transfer it. So this is called digital modulation. Please note, when we are looking at digital modulation, the common thing between digital modulation and analog modulation is that carrier signal stays analog, and that is the nature of carrier signal. So if I want to refer to the example that I explained to you, trying to explain what happens when you throw a stone on a water surface in a pond, how those waves are generated. The similar way the electromagnetic wave is generated. So that electromagnetic wave doesn't have digital format. That has pretty much analog format. It's not possible to send something that is 1 or 0. So we have that natural analog format associated with our carrier signal, no matter what kind of signal we want to send. So that would be a difference between the modulation that is analog and digital. We will look into some shift key modulation schemes later on. I will explain those. For now, let's just stay looking at analog modulations for now. Now, the definition frequency modulation FM says that the information signal varies the carrier signal within the small range above the original value. So when we are looking at frequency modulation, we are going to change the frequency of carrier signal. Remember, so far when we were looking at amplitude modulation, we were looking at the amplitude of carrier signal being changed. That envelope was changing the amplitude of carrier signal, but the frequency of carrier signal was staying the same as the frequency of modulated signal. In this case, we are changing the frequency of carrier signal according to our information containing or just data signal. Now, how we do that? We have this formula here, which I have omega t is equal to omega c plus k omega mt. So this is the frequency of FM wave. So if FM signal is generated by my mt, so I'm going to have the result shown as st, and that is going to have the amplitude AC and then cosine of omega ct plus theta mt. So you can see that we have characters that are associated with my mt inside my cosine, my sinusoid for my carrier frequency. Something that you can point out right away is that the amplitude of modulated signal stays same as before. So I'm not changing the amplitude in this case. I'm just changing the frequency, and I'm replacing it with components associated with my data signal. Now here I have a video that you can watch, and it explains the FM modulation furthermore in details. I'm just going to move on, and I'm going to explain based on these figures here. So it is a bit simpler compared to AM modulation in terms of, we don't have that shift happening inside our process. So the data signal is being multiplied in carrier signal in certain way. So if my modulated signal is shown by this blue wave here, and the red wave is my carrier signal. So if you remember the example that I was discussing in the classroom, remember I drew this wave here, and then I was comparing it this wave, and we can point out that this wave has higher amplitude to this. So the size, this one is smaller, this size is bigger, so that is known as amplitude. Another thing was the frequency. So the frequency of this signal is more than the frequency of this signal. The reason is because it is happening a lot more often, a lot more frequent. The phase frequency comes from that. And this is oscillating less often, so the frequency is lower. So the same thing I have here, the red carrier signal has a certain frequency. So I can play around with that. I can play around with how frequent that signal is oscillating. How we do that? Again, we are going to have something like an envelope. So that blue wave here is acting like my envelope. And then I have that signal, my carrier signal, being a little bit jammed, squeezed, meaning that the frequency is higher. When I have high or positive amplitude. So if you look at my wave here, the blue one, so in this case here, I have positive amplitude, so my frequency is increased. So the red wave is squeezed, and when I have my blue wave going toward negative side, my frequency is decreased. So the wave is expanded, so it's less frequent. The frequency is less. Again, when my wave is going upward to the positive side, to the maximum side of my blue wave, again my carrier signal is changed accordingly, and it is squeezed again, so a lot more frequency. Roughly, if you look at here, you can say that, okay, when my wave is positive, I have 1, 2, 3, 4, 5 sinusoids coming up and down. And when I'm on the negative side, I have only 1, 2, maybe 2.5. So you can see the different, what is exactly happening to frequency modulation. I hope this explains it well. One typical example of frequency modulation is just the radio that you can listen to, especially the radio in cars, not those digital radios that we can access through our phones, but the radio that we have in the car particularly. So when you tune two different frequencies, you're accessing each channel based on that particular frequency. And this is exactly how that signal is generated and sent to your radio. Now, again, I have this discussion about bandwidth. So how the frequency, frequency modulation bandwidth can be defined. So I explained to you that the carrier frequency on its own can be represented as a spike in frequency domain from frequency angle. And once it is modulated, the modulated signal has some side lobes. So in this case, because I'm playing around with the frequency of carrier signal, I am looking at a little bit higher bandwidth. So that bandwidth can be calculated based on the delta F and Fm. So that delta F is the variety of change. So if I have some plus minus that I'm playing around, remember this red sign. So for example, if that is F1 or FC1, let's say, and then I'm playing around with some delta F, let's say, I don't know, let's give it a quantity. Let's say 2 kilohertz, and then plus and minus. So I'm going up when I have maximum, and when I'm coming down, it will be 2 kilohertz less. So it is 2 plus 2. That will give me a nice variation. So that is my delta F coming here, and then the Fm is the frequency of my modulating signal. Again, in a very interesting way, my bandwidth has nothing to do with my carrier frequency. The reason that I emphasize on this is because many times students are confused between what is carrier frequency and what is the bandwidth frequency. When we are looking at different protocols in IoT, Internet of Things, we are going to look at the bandwidth of that signal, that protocol, and the frequency that that signal is occupying. So these are two different definitions, and I try to differentiate them every time when we move from one protocol to another protocol. And many times that bandwidth is kind of talked in a way that is associated with the speed or the capability of the technology that we are using for Internet of Things. I explained the speed or data rate in week 2 or 3, if I'm not mistaken. But again, as we move forward, I try to differentiate. This is the bandwidth, this is the data rate, and this is the frequency, the carrier frequency. So I hope that is explaining it well. Now, I have this exercise. I have just a typical sinusoid for the modulating signal. Let's call it mt equal to am cosine of omega mt. And you can, by just looking at that formula, you can know that the maximum and minimum of that amplitude is am and minus am. And the carrier signal is something like CT, a typical cosine wave. AC would be the amplitude, so it's oscillating between AC and minus AC, and the frequency is omega c. So how that modulated signal looks like? Can you draw that? That is the exercise. Okay, so I'll just give you a few minutes and then I draw it myself. Right. Just grab a piece of paper and try to do that exercise. And remember, we are looking at FM modulation signal. We are not looking at AM. The tip is start drawing your envelope as your dash line on your modulated signal, and then follow that pattern for your carrier signal, which is going to be modified to become modulated signal. So we can do it this way. You can draw axes and then dash lines for your maximum and minimum amplitude. Please do it while I'm drawing it. have another dash line wave added, and that is my modulating signal. It's going to act as my envelope. So we are looking at time domain, and we are going to change the frequency of carrier signal according to our modulating signal. At this stage, if you're confused, just stop the video and go back when I was explaining it a few minutes ago, and then come back at this point and start to do the exercise yourself. Okay. I hope you have done it by now. Alright. Okay. Your plot should look like something like this. So I have my wave squeezed. So that's where I have high frequency, and when it is expanded, I have my low frequency. The one that is down there, the dash line one, that is my data signal. I should have probably used different colors. Well, I hope this explains, and I check the video. If video is not clear enough, I probably draw it something on the screen. So that is the exercise. I hope everyone managed to get something similar to that. This part is this part and the one for last week. They are important. I'm going to have a final exam based on them. So if it is confusing or if you have any question, just feel free to ask me during the lecture time. Now let me see, do I have any more thing for this week, or I want to stop at this stage? I think I'm happy to stop at this stage, just making sure that we are familiar, all of us are familiar with how AM modulation is performed, how FM modulation is performed. And I might actually briefly explain the PM, the phase modulation, and then I move to the next concept. Okay? Thank you very much. Bye bye.